So again, predictive corrosion management using International Internet of Things, IOT, and digital twins. Related to CUI, it's Praful Sharma from Corrosion Radar. So whenever you're ready, Praful, I'll let you take control of the presentation. Thank you very much.
Thank you very much, Martin. Are you able to hear me all right? Just checking.
I can hear you fine, yes, and I can see the presentation on the screen.
That's great. So thank you for this opportunity. And this is a great forum. I see a lot of the people, colleagues whom I worked with in the list. So that's great. And hi to all. This is Corrosion Radar. My name is Praful Sharma, CTO of Corrosion Radar. So any technical queries, I can definitely answer them. I'm also joined with my colleagues Shiraz and James on this panel today. So any questions we'll see. So the context of this is CUI and digitalization. So digitalization in corrosion management is a big area, and predictive corrosion management is being termed as the next era, using industrial IoT and digital twins and how it is applied to corrosion and insulation. So just to set the context, I think the previous presentations were, great from Sonomatic and GE, and they were on inspections and digital twins of inspections. And now we are getting into monitoring part, where online monitoring, how it augments the inspections. Mainly online monitoring can be a screening tool where people can screen a large amount of data and volume of the assets in real time. And once there are some issues or risks are flagged, then we go back to that particular area and do the actual inspection. So that's the context here. So the agenda is for today is introduction, why we are talking about monitoring, the solution which we Corrosion Radar provides, what is it for, especially for CUI, some of the case studies where it is deployed, how do we do ROI calculations, because in digitalization process and industrial IoT, where sensors are involved, what is the return on investment? That's a very peculiar calculations, and the next steps as well. Say what it takes to do a next steps and installations and probably trials and large scale deployments. And we are working with many of the people who are already on this list today. So why we are talking about monitoring? So let's see the era of inspection 4.0. Now this is one of my favorite slides, because this talks about not only the past but the future, the era of inspection 4.0. So people call industry 4.0. When we say industry 4.0, anything related to manufacturing automation comes into that category, because the sensors are becoming cheaper, deployments are becoming very handy with battery powered devices. So that's becoming a reality. But what it means to inspections, so it goes back to inspection 1.0, where probably 6 decades back, where main method of handling it was leaks. Of course, the industrial assets were not aging at that time, so it was okay because limited leaks being handled. But then came the era of 2.0, inspection 2.0, where somewhere in 1980s, 90s, where electronics started to get developed, techniques started to be developed, portable instruments, and that continues and carries on in the various geographies. And then somewhere in early 2000s, inspection 3.0 came in, where it was more about optimization of inspection process through statistics, to risk-based inspections, RBI processes. Of course, Shell was a pioneer in that as well, and that's been the main method right now. But in many places, it's proven that RBIs and all these practices have not worked. We have now great experiences of implementing RBI in many places, but now people are resorting to some of the places where RBI is not applicable, stainless steel or even towers. So the next era of inspection is inspection 4.0. At times I make a bold statement there as well that, when we say inspection 4.0, it means no inspection at all. It's all automated and directly maintenance of using sensors and automation. And that's been the case for, say, in controls. People do automated controls. There's no manual human needed there. It's all automated. So why not in inspections where we get directly from the sensor data place where maintenance is needed? So that's the next steps. So manual things are becoming automated, detection is becoming prediction, and reaction is becoming prevention. And we are already seeing that happening in many different inspection techniques. For example, ultrasonic wall thickness was one of the earliest ones which became monitoring, and now it's being automated, and that philosophy is coming to other places. So what's the opportunity here for all of us, for this community, is predictive corrosion management, a massive opportunity for improvements, safety, costs. And this can be enabled by industrial IoT. Industrial IoT is a term derived from IoT, which is a common term which is being used in domestic circles, which is Internet of Things, where cheaper sensors getting connected wirelessly and then being shown. So all that is available now. And now the power is, how can we use this large amount of new data getting created with prediction abilities? Can we analyze them in a very automated manner and give insights? So on the left hand side of the screen, you see the current practice, which is more reactive. And this is applicable to all the inspection processes, not only the CUI, which we are going to talk about, but also to other types of corrosion. So it's mainly human judgment, often a lot of guesswork on the risk. Periodic manual inspection is the main method, where visual periodically inspections are done. So reactive maintenance, it's still labor intensive and risks are still high. So we still hear about a lot of accidents. But what is happening now is the new era is coming with the sensors and connectivity, wireless connectivity, and combined with the knowledge base and analytics, a real-time monitoring of issues is possible and being provided now, starting with ultrasonic wall thicknesses, and now we are going to talk about CUI right now. So it's a predictive maintenance strategy where well in advance, early detection of issues. For example, rather than directly talking about parameters of the pipe, say wall loss, which has already happened, can we monitor the conditions which leads to those wall loss, say water, moisture around the assets, etc. So indirect parameters which are precursors of corrosion. So that leads to predictive maintenance, minimizing labor, increasing safety. Obviously, the first application, a major application we are talking about as corrosion radar, we're talking about corrosion under insulation, because that's the first target segment for us. And the reason is it's obvious. It's among the top, or many times it's number one asset integrity issue. Majority of the pipeline failures are due to CUI in oil and gas industries. And when we talk about offshore platforms, a significant amount of maintenance cost goes to CUI, and we have seen, even as recent as probably last year or 2 years back, we have seen big, major, high-profile cases in offshore where shutdowns has happened, and in a production loss, which at a large scale has happened. So this audience does not need, I think, introduction to CUI. CUI, we know it's due to water ingress or condensation. Ideally, it is we have to seal all the insulations or remove the insulations where it is not needed, but seal it off, have the coatings, but still CUI is happening. The problem is it's unpredictable locations. Spot techniques are great, but spot techniques like pulse steady current, X-ray, or even visual inspections, the problem is such large, huge, that spot techniques cannot scan efficiently in all the places where we want. So still we have to do a very subset of inspections. Can we have a screening technique which tells us when and where the risks are, and we do inspections at those locations rather than blind inspections at 100% location? So one example is, if say in a cycle of 7 years or 8 years, you have to strip off 100% of the insulation. Can we go from 100% insulation removal to probably 2% or 5% insulation removal? And those are the locations where the tools will tell those are the risky locations. So when and where screening techniques, that's the objective here. I'll come to corrosion radar system in a minute, but the reason why we are talking about is because there are huge cost savings in a life cycle of a turnaround. We are talking about probably upwards of 30% cost savings and huge risk savings, because risk is the main deal here. Human lives are at stake. So that's the benefit of monitoring system. So this brings me to the next stage, where what are we talking about? Solution. So corrosion radar solution is about predictive corrosion management using industrial IoT, the first application being CUI. There are three parts here, three pillars of an industrial IoT solution as we talk about. On the left-hand side, you see detect pillar, which is more of sensors. Today, we will talk about corrosion and moisture sensors, which I show here, corrosion and moisture. They're unique sensors in the form of wires which gets embedded inside the insulation. But in the future, corrosion radar is working on various other types of sensors, like coating sensors and various kind of other sensors on different principles. So we are not limited to CUI, but other aspects. On the middle pillar is about electronics and wireless transmitters. So the electronics gets connected to the sensors like this blue box, and wirelessly transmit data using various industrial IoT protocol. Again, I'll talk about that. And you can remotely see the data on your dashboard, basically on the. I'll show the dashboard or web page in a minute. On the right-hand side is predict pillar, which is the exciting part about our analytics, and that's where the power of data is. That if you monitor moisture, it does not mean you just get information about moisture. You get information about various aspects, like what is the potential likelihood of corrosion rate, what is the coating life reduction, say if you have models, what is the risk to stress corrosion cracking, etc., so and so forth. So the combined corrosion and moisture can give a whole lot of information, whether there is a risk of chlorides, because chloride leads to a lot of accelerated corrosion. So corrosion rate may be high there, and moisture presence. So this leads to a better understanding of the assets, as well as gives more predictive ability, that the more the data, but the better you're able to manage it. And we'll talk about three different platforms we're building. CR Cloud, which is cloud-based platform. On-premises means on-premises data and software, and the digital twin, which we will see a glimpse of it today. So this brings me to the first pillar, which is detect, and that's about sensors. So in this case, corrosion and moisture sensors, two different sensors for predictive CUI management. So you see the pipelines, the orange color indicates sensors, which are in the form of wires. It looks like optical fibers, but they are not optical fibers. They are more of microwave waveguides. The principle is called electromagnetic guided radar, EMGR. And the sensors are deployed inside the insulation, embedded into the insulation in various fashions. For example, if it's a small diameter pipe, we'll put the sensor and the linear at the bottom of the pipe. But if it is a vertical pipe, or large coverage is required, like large pipe diameter, we'll prefer a helical configuration. Now, as far as pipe is concerned, that's the arrangement. But if we have towers, the rings of the towers are very, very prone to CUI, and then we have cases where we have put rings around the ring of the tower, and then a large area like a heat exchanger or any pressure vessel we cover in a mesh configuration in a zigzag fashion. So the crux of the sensors is embedded sensors, long range modular, can cover complex geometries, because effectively this is like they are installed like a heat tracing system, and installed in a very similar way, even going around flanges and bands. It is installed in a very similar way. So as far as the principle is concerned, the corrosion sensor is it's a multi-layered structure of wire, and the outermost layer is sacrificial. So sometimes I call this is the longest coupon in the world, where you put carbon steel layer inside an insulation, and wherever water is coming in, it starts to corrode. And then the second problem, when you have the largest coupon in the world, longest coupon in the world, is where that coupon is getting corroded. and we use electromagnetic radar principle for that. So we send microwaves inside and using time of flight locate exactly where it is. So that's on the corrosion, and moisture also follows the similar principle without the sacrificial layer. So the moisture does not have any sacrificial layer, no metal component. At a time, 100 meters for corrosion sensor and 50 meters for moisture sensors, and up to 300 degrees Celsius capability. So that's on the sensor side. The principle, as I mentioned, is electromagnetic guided radar, EMGR. It's a patent pending technique where the core sensing principle is, if you see this black cylinder as a pipe, we lay the sensor next to the pipe or near to the pipe or even embedded into the insulation. And on day one, you take a baseline, you see the signal here is not showing any indication, but over time, there are two locations where we start to see reflections. That's where either water is coming in, or in case of corrosion sensor, the corrosion is happening on the sensor, so sacrificial. And we monitor this over time remotely using databases, and you get to know that, okay, these are the locations where needs to be watched out for in the next inspection. So in the next inspection cycle, you will either strip off at that particular location rather than all of it. So this brings me to the next one, which is Connect Electronics. Now, this is how it looks like, the ATEX compliant product. In this case, we show battery powered unit as well, which is available as well, but electrical power is works for we don't have any limitations on that as far as battery life is concerned. So electrically powered. Now this is for zone 1. You can see the antenna here, which works on various protocols including Wi-Fi and cellular, which is more useful for a smaller scale pilots, like probably 6 to 10 units. But when we go larger scale, the cellular connectivity and Wi-Fi, we prefer wireless HART or LoRa. So these are the 4 capabilities. And of course, there are places where there's no wireless connectivity. So we have provided manual data collection using ATEX certified USBs as well. So this is on the electronics. The third pillar is the predict analytics platform, and that's where the power of industrial IoT and digitalization comes in, because the data is coming to your desk. So here there are 3 platforms on the top, which I show. One is the CR Predict Industrial IoT Cloud Platform. It's a web page based system where the data is being shown and analyzed. I'll show you a glimpse of that. The next one is shown here is the on-premises, because many of the end users, they're not evolve their policies around data on the cloud. So on-premises may be a better solution. So we provide software and data connectivity to that. The third one is, why do we want to see the data in 2D format? We can show the data in 3D format. So that's where the digital twin platform comes in. And I like the first speaker, Victor, said that there are many definitions of digital twins, but the real definition comes in terms of whether it is are we talking about 3D models as a digital twin, or are we talking about that predictive ability from a digital twin? So in this case, it's both. It's not only 3D visualization, but also predictive ability, where the predictive algorithms. So if you fast forward into the future, you'll see the color coding scheme change over time, that where the corrosion is likely to be, depending on the corrosion rates of the sensors. So it gives a very high level good view. So it saves a lot of time for inspectors to actually plan the inspection, because now this is a great communication tool and prediction tool. On the bottom, we are showing different types of examples of different modules which gets add on to any of these platforms. For example, analytics module for more analysis, prediction module for example, corrosion rate estimations, or even automated defect recognition using machine learning, where we detect issues and flag it in the system automatically. So that this is an example of the going into details about algorithm product. Say predict corrosion rate. In this case, this is an example of laboratories where we have various third-party laboratories, including some research laboratories, universities, and our in-house laboratories. So we do a lot of testing in this. Say ASTM G189 shows that if you have a pipe, in that we put a sensor and we let it corrode. We put the coupon as well to monitor the weight loss over time. and we benchmark it with API 581 or similar, say DNV models or API 581 models. Of course, there are a lot of variabilities. Not a lot of people agree to API 581 as well, but and we tend to see a lot of variability as well. But that's the best set as of now. So we try to estimate the corrosion rate, and in a lot of cases, when the conditions are matching right, we see a lot of similar ballpark figures on the corrosion rates. So that's a validation scheme. If you have a specific pipe carbon steel grade which you would like accuracy of corrosion rate, then we can benchmark that, as a joint case. But we have baseline models available. This is another algorithm as a product where you can have automated defect recognition using machine learning. Now, I'm not going into details of this software at the moment, but just give an example that you put into the data and automatically we get listings of where the corrosions, which tags corrosions are showing at what locations, and warnings, etc. So it's a kind of large scale automated analysis system where manual analysis is too limited. So those are the products. And now it brings me to the third place where the case studies. We will show the case studies where it is deployed. Some of them, actually, many of them are deployed at locations and companies which are attending this this meeting. So grateful to that. So let's go to case study A. Production column corrosion monitoring using ATEX system. Now, column is a big use case for us because the inspections are very difficult, and RBI normally is very limited in these kind of applications. So our sensors, because of their flexibility, they are very unique for these particular applications. So in this case, the example is on this particular tower production column. It was going through a turnaround every few years because this is a very old asset. So every few years they go through a turnaround. I think probably 5-6 years. They build a scaffolding, and scaffolding is very, very expensive. Most of the times they don't find CUI, so it's a wasted exercise. But if they find CUI, it's very localized. So the partial stripping is not an option here. So it is a huge expense. So they said, okay, can we do inspection only when it is required? So moving from periodic inspection to condition-based inspection. Now, if that needs to happen, you need to have a monitoring system in there. So we got involved, and the customer highlighted that at the top of the tower is the history of CUI. That's a very likely location, and the bottom of the tower is also likely location. Ideally, we should cover it 100% over from top to bottom. But in this case, they wanted to limit because it was short time scale and budgets discussion. So we limited from top and the bottom. We selected helical configuration, as you can see, because of the geometry here. The orange colors show the sensors on the top, and they are connected using bridge cables, about 17.5-meter bridge cables, to the electronics which is placed in the middle. Now, normally there will be multiples of these boxes to cover the whole asset and to have the risk. But in this case, 50 meters at the bottom and 50 meters to the top, total 100-meter sensors was used here. The electronics is zone 1 in ATEX. The wireless transmission is using cellular network in this case, and you can see the 2 channels here. Now, in this case, the asset was painted and sandblasted and painted, refurbished, but still there was a need for this monitoring system because the trust in the coatings was not high. So in the past, this asset had the coatings, but even then it developed CUI. So that's an example here that even if you have a preventive measure, a monitoring system is needed to ensure, as an assurance tool, that there's no water in and there's no corrosion getting developed on the sensors, which is indicating the risk to the assets. So if it is, then it is a risk to the coatings as well, and the consequences are just too high. So you see the sensors being installed here, and the insulation is again reinstated. And now this is being monitored. It's been a few years now to that we are seeing this. Case study B. Again, kind of this was a trial where you have the most important picture is figure D, where on the bottom right, you see moisture sensors and corrosion sensors. In this case, they are installed one below the other, but it need not be the case. They can be installed together. But in this case, the moisture sensor was more likely to catch water if water is added. So we put it right at the bottom. It's installed in a very easy manner. On a normally it takes half a day for installation. In the previous case, this took half a day for the corrosion sensors, moisture sensors to be installed. Again, similar case here. So it's not a very time-consuming activity if it planned well. And this is how the data looks. A typical data, we show it in form of B-scan, where the x-axis is the date or say time, and the y-axis is the distance along the sensor. In this case, the sensor was shot between 20 and 24, and around 22-meter location where you saw that flange, where you show that open cutout, it was closed. And then we started to see patterns of water coming in and going out, and there was large period of dryness. And this correlated well with the amount of rainfall in that region and pointed towards that probably there's some opening at that location where rainfall is coming in. Normally, this kind of data is not available. I mean, people will assume that the insulation is great, insulation is all sealed off. But because of these conditions where water is coming in, the CUI happens. And that's what we're trying to catch here. Now, there are multiple uses of this. The basic data is about moisture detection and location. So localization tool, screening, that this is where the water is. The second is the periodicity of the water, which is actually another level of risk. If it's periodic, then it's very detrimental to the coatings because chlorides tends to get deposited. The third angle is the prediction. Say we take this kind of data and put it in our prediction tool, say using models, corrosion rate models, and estimate in the worst case scenario, if the coating is damaged, what is the corrosion rate here? And other uses of this data is the coating risk. If the water is coming in here, what is the risk to the coating, the life of the coating? And if this is installed on stress in stainless steel pipes, then we can even prevent stress corrosion cracking altogether. So who wants an inspection? Why do we want cracks to be developed? If we can avoid water, we can avoid corrosion. That's the philosophy here. Again, case study C is on a complex pipe network. You see somewhere in Asia, monsoon season. So the pipe is complicated here. So the corrosion and moisture sensors were installed in parallel along this pipe circuit, about 10 meters each. Normally, we can have like 50 meters, 100-meter corrosion and 50 meters moisture, but in this case, 10. And the data seems data was quite revealing. And over a period of time, after 6 months, you see the top plot is showing the raw signal of corrosion sensor. So the black line is the baseline on day 1, and red line is the after 6 months, almost matching, nothing, no corrosion observed. But in case of moisture sensor at the bottom, you see the red lines. There are some indications, very minor indications starting to happen that water is coming in. And if you map it to 3D model, on the left-hand side, this is somewhere at the bottom of this pipe is where that is mapped. And that's the power of this data, that you can map it to various locations. Jumping to 9 months, after a while, after say monsoon season was over, corrosion was detected at multiple locations and water was indicated at multiple locations. Now, bear in mind, on the left-hand side, you see corrosion on the top and also mild corrosion somewhere in the bottom of the pipe, and moisture being stagnated at multiple locations. Some of them where the corrosion is happening on the sensor, but some of them elsewhere where in the future we will see corrosion. Now, there are multiple angles here. One is this shows to the end user that rather than periodic inspection, they're already seeing corrosion, say water coming in. So they should be inspecting it at those particular locations at the next cycle. Of course, with corrosion rate, they can get that risk as well. The second is, if this would not have shown any water, we would have not recommended any inspection at all. So they would have saved cost of inspection, unnecessary inspection. So both ways. But in this case, since a highly localized region is identified, probably they will do a very precise inspection, say either visual inspection or using pulse steady current or X-ray at those locations. And that's the power here, that this is a pre-screening risk-based risk identification tool, and then a validation is required. So normally, so why we should do this? Because there is a return on investment, and normally we get involved with the end users to talk about return on investments. The benefits of corrosion radar system is the corrosion and moisture sensors, when they are working together, you can have a data-driven RBI. Normally, RBI is a design-driven activity with very little field data, the real conditions of the asset. But in this case, you're getting direct data-driven RBI, where data is being fetched, the condition of the insulation, the moisture sensors, indications, etc. They get feed into here, and then that reduces the risk and probably optimizes the inspection procedures, leading to predictive maintenance and CUI prevention. But even if you don't have RBI, in most cases it's not. Early detection leads to better management of the assets and predictive maintenance, and that's what our objective is, to give you more data. So what entails? We do a lot of pilots with first time with a lot of end users. We have done many. So normally, what comes to about is selection of the assets. These are the examples of some of the assets. A combination of them is selected normally, because the applications and value case is different for different applications. So in this case, an example is a small diameter pipe, 4-inch, 100-meter section. Asset 2 example is about 8-inch diameter pipe, again 100-meter section. The third asset, as an example, is a horizontal vessel. Fourth one can be, say, vertical vessel. So the use cases are different, and normally we work with end users on this. Then we get involved with cost benefit analysis, and this is an example of that. One of the cost benefit analysis. They normally we get some inputs, work with the asset owners as to what is the length we are talking about, how much cost per unit inspection is spent already, what is the inspection cycles, inspection percentages. Normally, people don't inspect 100% all the time. They go for subsections based on risks. So what is that looking like? And with corrosion radar, we can reduce that to a fraction. And how does it boils down to with and without corrosion radar, with and without monitoring. So this we get involved, and we can help you with that, making a case for that. So this brings me to showing the digital twin version, where once we install the sensors, we are working with various the digital twin suppliers, where we don't give 3D models, we don't give digital twins ourselves, but we enable them with a color coding scheme. So we are working with, for example, Aviva and say Dassault Systems and many more. So in fact, we have worked with Sonomatic as well. We've done one project with them. So we work with digital twin providers to enable the data. So in this case, I'll show you an example of what it entails, how it should look like. So let me fast forward. So if you see this, I hope the video is smooth, but if it is not, if due to data, probably it's my apologies. But in this case, you see the plant model, and the sensor systems are installed. In this case, you see corrosion radar, and the sensor is installed in a linear fashion on a carbon steel, as an example. The data gets transmitted over time, and once the data is transmitted, it is being analyzed remotely in a dashboard, and then a local region is identified where this corrosion is developing, say either moisture or corrosion, depending on the sensor, and then this location is identified in the model as red. So this gives a very quick understanding where that problem is located, so that communication wise, you have a huge time advantage of communicating to the integrity, asset integrity and inspection teams and maintenance teams. This is another example where, say, in a tank, a specific region, the sensors are installed, and normally this will go through periodic inspections. But in this example, hypothetical example, it's green color, which means it is okay. There is no corrosion indication. There is no moisture, so no action is required. and you save cost in the process. That okay, if there's conditions are good, why we should inspect. Another example here is corrosion radar sensors being installed in a helical fashion because of the complicated shape. Customer might decide that okay, we want more coverage, so let's install in this manner. And unexpectedly, I would say the top regions of this pipe is showing yellow indications, which means probably some kind of moisture accumulation, which is not an expected region. Normally, you would expect it to the bottom part. So that is an advantage with that system, that it gives the data. This is an example of large surface areas like a heat exchanger or a pressure vessel, where on the outside you install the sensor corrosion and moisture, and based on the data we localize where it is, when and where to do. We also propose this for pressure vessels where it's to be inspected every year. But if there's no water, there's no need for inspections, and that's our case. That let's avoid water, let's ensure there's no water, and that gives us an indication of need for no inspections. So this is a high-level helicopter view of the asset, that the color coding schemes tells us where the risk of the CUI is. Let me go back to that, where the high-level risk of the CUI is, for example, some of the locations where it needs to be done and some of the locations where it should not be done. So that's a digital twin version of it. Now this is the third angle where it's more about data visualization, but what I have not shown is the past and the future of this. For example, if you see this view, and we have a scroll bar where we scroll the futures, if next 2-3 years or 5 years, how the color coding will change depending on where the water is and what the temperature profile is, etc. So the future is predicted, and also historical data is anyway logged, so we can go past how in the past it has changed. So that's a digital twin version. Now, what I would like to show you is how this system gets installed. Let me show an example of cladding and insulation on a vessel where it is a foam glass insulation. It's for cold operations, say below 0, -20, -30 degrees Celsius. In this case, the foam glass is used, so the sensors is installed inside, both corrosion and moisture. So in this case, the orange is corrosion and blue is moisture sensors. They are getting installed in a helical arrangement. And let me fast forward here. So then once the insulation is installed, the sensors comes out in a particular arrangement. They are sealed. They're sealed with conduits, and there's a junction box which comes out. Now the important part here is in the junction box, the sensor gets connected to the bridge cables. Now the bridge cables connect to the electronics box, which called nodes. So bridge cables allows us to place the electronics remotely to the assets. So we can be up to about 20 meters linear distance away. So it gives us flexibility where to get installed. The electronics is 8x rated in zone 1, so it is quite flexible where it gets installed. So that's the installation procedure, I would say. So coming back to how we can help is predictive CUI monitoring system. We do cost benefit analysis and risk return on investment calculations with our end users. Talking about pilots, from pilots to scale up, all the discussions, what it takes to take a pilot, and also consultancy about digitalization and predictive corrosion management. There are so many things happening, how we can help, where it is more impactful, where it is less. Organizing a dedicated seminar for your company, we normally do that so that a wider audience gets aware of the benefits and the systems. And also our business model is attractive in the sense of either is a capex expenditure or even operational expenditure based on service models, whichever suits you. For example, data as a service. So we're still discussing this with various end users as to what suits them, so that the deployment barriers are removed as much as possible. feel free to contact us at info@corrosionradar.com, and we'll be happy to discuss these various aspects. So that's from Corrosion Radar, and open to questions.
Thank you very much, Praful. We're welcoming questions. Please feel free to use the chat as well if you want to propose a question. There is a question there from one of the guests. It's to do with the life of the sensor. What is the life of the corrosion sensor when there is corrosion compared to the expected life of the pipe?
Yeah, so that's a great question. I think the sensor, the moisture sensor is the easier answer here, which is, let me go back to that slide. Yeah. Here there are two sensors, corrosion and moisture sensors. The moisture sensor, they don't have any corrodable, corrodable layer. So our estimate is we are not deployed it for 15 odd years, but our estimate is more than 15 years for moisture sensors, which should last about more than a turnaround in the worst case. So that's on the moisture. Now coming to corrosion, corrosion have a sacrificial layer on it, which is a corrosion sensor. Normally when a spot is getting corroded, it continues to function even beyond at the other spots, because the wave gets partially reflected from one location, and the other locations are continuing to function. So at that time, the sensor have corroded at a particular spot. Either it can be refurbished by cutting it, connecting a new one when an inspection is being done, or because it's a connectable modular system. But if it is no action is decided to be performed, then it can be left as it is, and it should continue to perform more than, our estimate is about 10 years, that for 10 years there should not be any problem if there is no corrosion. Even if there is a corrosion, it can be left, and the other areas should perform well beyond 10 years. So that's our estimate. Of course, we have done accelerated testing on that, but not deployed for 10 years as such. So I hope that answered the question.
Certainly, yes. More questions? Certainly, Mark, far away.
Hi, Praful. Your predictive model basically uses the sensors for water and corrosion. But if you actually do an inspection at some point and get real information, maybe from visual and more detailed inspection, or even perhaps from NDT, do you have a way of updating the predictive model so that it takes on board the sort of actual condition over time, so it's not purely reliant on the sensor inputs as a basis?
That's a great point, Mark, and my answer is, yes, we have built in a flexibility here. So this, what you see on the screen is an API 581 model, which includes many factors. Now these factors are subjective to where the asset is located, for example, near the coast or tropical regions. And this is a highly variable parameter, because if it's a salty condition or it's arid conditions. Now we take best judgment when the baseline corrosion rates are being estimated for moisture sensors and corrosion sensors. But if there's a field data coming in, say inspection is done, then we readjust these parameters to actually calibrate that. Okay, now we need not rely on the API 581. We have the real data, so the parameters, the parameters are adjusted, and we get a more realistic feel of the corrosion rates there. Of course, CUI is a highly variable corrosion rate, so we have to have many data points before freezing on narrowing down. But yeah, so that's how we build the flexibility here, by changing the parameters of the corrosion rate if the real data is available.
Okay, thanks, Praful. I think it's really important to be able to use the inspection information, when you can get it, as a basis for updating the predictive model, because that's kind of the only real information that you have for validation. And even that might have limitations around the technique that you use to collect the inspection data.
Yeah, absolutely. Absolutely. But the highlight of this, what we're trying to do here is the localization of the risk. Now, this is not a quantification tool. This is not an This is not how it is posed. This is a localization tool. Say if you put a sensor, it localizes, okay, that's where the problem, that's where the risks are, and when it is happening. So when and where, but the quantification needs to be done with the proper NDT instruments, say ultrasonic or guided wave, once we localize it. So it's a combination always. But it's useful to know rough corrosion rate so that you know how much time window you have.
Thank you.
Yeah, thank you, Mark.
Another question on the chat line, Praful. What's the surface coverage either side of the sensor wires? Is there coverage overlap, or is the sensor only reading the line under the wire in direct contact with a pipe? Apologies, the questioner might have missed part of the start of the presentation.
Yeah, well, I mean, the question is very relevant here, that the sensor is a I would say is a proxy. In the beginning, I introduced this as a corrosion sensor as the coupon, say longest coupon in the world. But so when the water touches the sensor, then it gets corroded. So if the sensor is placed at the bottom of the pipe, it is representing an area at the bottom of the pipe, not necessarily at the top. So if a large pipe diameter, we want to cover the top as well, because the water can not stagnate at the bottom, but it can be stagnated anywhere in the large pipe diameter, then we tend to go for helical configuration. And this is always a discussion with the end user, users on what is the best configuration. So I think I'm hearing an echo in the line, but yeah. Yeah, so just to answer it short, that the coverage is dependent on the type of asset. The sensor tends to detect only the conditions around the sensor. Say if water is present and touching the sensor, then and the condensed water, it detects it. If it is far away from the sensor, it does not detect it. So the layout and the deployment is a close coordination with the end user as to what is the best configuration here. So yeah.
Can I ask a question?
Sure.
Yeah. Hello, Praful.
Hi.
Thanks very much for the let's say showing the integration of the sensor, making it a predictive tool. The scale of the corrosion installation problem is so huge in terms of square meters, and what intrigues me is you showed connecting it to a digital twin. Can you elaborate a bit on what is going in a digital twin? Do you rely on, let's say, an established digital twin of a operator, and you add tools to that to cover it everywhere where you want to do this monitoring? How does that work?
Yeah, so there are independent systems. One is the detection and connect is the hardware and elements, and then on the right hand side is the predict. If you see the screen, either we give normal softwares like cloud and on premises with a database, or if it's a digital twin, then we tend to work with an existing digital twin of the asset. We don't create a digital twin, but we feed the database into that digital twin, and this is very much doable with the connectivity of the database. For example, the existing assets, many of them have been using digital twins provided by various companies like Aviva. Aviva uses a color coding scheme of their assets of the pipelines. Now, if our data is linked to their database of the color coding, then the color coding is done based on the severity of the CUI, and that's the idea here. So Seeger, the short answer is we tend to work with the existing digital twins of the assets. So we feed the data into it, but that's the end result. But before that, there's a even basic monitoring is what we do.
Yeah. Okay. Thanks very much, Praful.
Thank you, Seeger. Yeah. So any more questions, and we'll be happy to answer that.
Certainly, yes. Sorry, I was muted temporarily. Two questions on the chat. From you and from Shell, what success have you had with the sensor so far?
Right. I mean, with Shell, we are still working on potential use cases, trying to propose various applications, including moisture sensors, because I think Shell have this vision of having moisture sensors already. So it's a work in progress. I would not say a lot about that at the moment, but there are published use cases with other operators we have published in the public domain, which are available on request. We can send some good case studies where the deployment have been done. So for some of the case studies which I've shown, they are more public information, but many of them are confidential at the moment.
A second question from Raphael. Could you tell us an average ROI estimated or achieved so far? I'm assuming that's reduction inspection. Raphael, please correct if that's not the case.
Yeah, so that's a great question. I believe my colleagues are also on the call today, James and Shiraz, and if they would like to comment on any particular aspect, because they get involved in a lot of ROI calculations. But what I would like to show is if we take a typical ROI, we did it with one of the operators in, this is an example of an offshore unit, not an onshore, but an offshore operator. It showed over a 12-year cycle about 60% for a pipe, 60% ROI, 60% cost savings over a lifetime. So this is how the plot may look like. Say initially the blue dots are say corrosion radar system, the cost with corrosion radar system, and the red bar is with the without monitoring. So with the usual inspection cycles of say 10 to 20% of inspection every few years, 4 to 5 years, and in 12 years 100% is strip. So can we remove that, reduce that extent of insulation strip by putting a monitoring system, and over a total overall lifetime is about 60%, and depending on the asset it can vary from probably from 30% all the way till 60%, depending on whether the criticality of the asset and the costs involved in inspections, etc. We tend to get involved with that. So that's a typical range, 30 to 60%.
Okay, thank you, Praful. There is one more question here. Apologies, our ROI is obviously return on investment, which you ascertained very quickly.
Oh, right, yeah.
Yeah. A question here. Are there any publications available now or in close future to understand more about CR system technology and ROI?
Yeah, absolutely. We have published it. Actually, even in this month in one of the magazines, Corrosion Management magazine from ICOR, there's a technical article published where we have described the whole technology and applications and ROI calculations as well. So upon request, we can send it. Definitely, we can send it. So please send us an email on info@corrosionradar.com, and we'll send you the article, technical article, which can be provided.
Okay. Hi, yeah, if you can hear me.
Yes, certainly, yes.
Hi, Shiraz. Yes.
Hi, this is Shiraz, the CEO of Corrosion Radar. Just to add a little bit on that, I mean, ROI, we have a calculator that allow us to calculate the ROI for specific assets. So if anyone has already some data about specific assets and how much it's costing them now, and kind of drawing, we can quickly answer that question for typical assets and give you the information to compare the benefit of deploying such a monitoring system.
Okay, two more questions. Does the model take credit for the condition of any applied protective fabric coatings at time of installation, or is the model based on indicative corrosion rates of the corrosion radar sensors only?
So, so the corrosion rate from the moisture data and the corrosion sensor data is about corrosion rates of our sensors. And as far as moisture sensors is concerned, it uses the existing models by API 581 and other, say DNV 109, etc. but they provide the worst case scenario. Like if you have a coating, the philosophy here is no water, no corrosion. So if you have a coating and there's no water, this can tell you that there's no water. So no need for an inspection. That's one. But if there's a water there, the corrosion rate we are providing is on an assumption that the coating is damaged, because that is the worst case scenario, that coating gets damaged and the metal is exposed. In that scenario, what is the worst case corrosion rate? And that's what we have to assume when we have to probably inspect it, because that's the worst case safety critical assets. So we give the worst case scenario when the coating is damaged. But also, other than the corrosion rate itself, what we also provide is a other model, which is the risk to the coating life. Say coating life, if it is long, high, ideal, but if water is coming in at a particular temperature, probably it reduces to medium life. And if it is a cyclic temperatures, and cyclic temperatures, chlorides, probably it is very, the risk to the coatings is very high. So we categorize them in that sense, and that gives you an indication as to what might be the coating risk. Again, applications to stress corrosion cracking as well, of the moisture sensors. Now, in that case, it's not a coating, it's not a corrosion rate, but the risk of SCC. Nobody wants a SCC, but if the water coming in, that's not desirable. So knowing moisture sensors and the risks to the SCC. So other than the corrosion rate, which is an estimate, the various other insights are being observed from moisture sensors. So sorry for the long answer, but I just wanted to say about corrosion rate, but beyond as well.
Okay, two questions. We'll probably have to draw conclusions soon. Hi, Praful from Chris Gales, HSE. Thank you for an interesting presentation. Is it possible to remove the installation to allow accessibility for alternative inspection techniques, for example, UT or radiography for internal inspections?
Thanks. A good question. Again, I did not touch upon this point, and I'm sure my colleague Mehrdad is also on the line, who leads the deployments teams, that the best opportunity to deploy is when the insulation is already getting removed during a turnaround or an inspection cycle. But once it is installed, coming to the question here, can we use different techniques like ultrasonic and X-ray to do the inspection? So answer is yes. I mean, this is like a heat tracing system, which is always present. And we select the locations. Everybody selects the locations where inspections can be done, like ultrasonic spot. And this is no different. This is installed and looks and feels very much like a heat tracing system. So the answer is yes. It is not very intrusive in other inspections whenever it is needed.
Okay, one more question here. Do you get pipe temperature from the sensor?
Well, I mean, that's our wish. At the moment, we don't have that capability, but we install other types of sensors, wireless connected temperature sensors, which gives that ability. If there's a need, we can discuss that. But inherently, corrosion radar sensors are not capable of temperature sensing. We need other sensors to integrate in our system, and we can do that.
Okay, well, thank you very much, Praful, for an excellent talk and for all the very useful question responses. If a question occurs to anyone after the event or later on any of the talks, feel free to type it into the chat. Just rejoin the meeting, type it into the chat section, and we'll seek to get an answer from the relevant speaker. Thank you all for attending. Sika, would you like to give a closing statement for the seminar?
No, only I want to say a big thank you for the presenters for their very interesting presentations. I think they have given us great insight in what can be done, and food for thought, I would say. And I hope we can progress this fruitfully in the HOIS digitalization project. Thanks very much for the presenters.
Okay, for those who had been hoping to see the fourth talk from Gareth McIntyre from GDI, unfortunately, for personal reasons, Gareth wasn't able to give the talk today, but he will be scheduled in the next forum as a speaker, which we hope to have sometime after the HOIS meeting, probably early in July. So thank you all very much for attending. We have been recording the seminars. Once we'll check with the speakers that they're happy, and we'd hope to circulate to attendees and to hoist members in general the links to the recordings and also the presentations themselves if the speakers are able to make those available. Okay, thank you very much.
Thank you, everyone. And
Yeah.
thank
you.
you.
Bye-bye.
All right. Thank you.
Bye.
Goodbye.
Thank you, everybody. Bye.
Thank you. Have a good afternoon.
Thank you.